Welcome to the second half of section 8.2. Let's start with a warm-up. Let's write this power series expression as a single power series in x to the n. I suggest you pause the video and give it a shot. So the first thing we want to do is start by re-indexing both power series. So we want them both to be written in x to the n. So we need to add 1 to the exponent here, which means down at the base, we're going to subtract 1. So this one's going to start at 0. And then it will be n plus 1, cn plus 1, x to the n. And then this next one, I'm going to bring the 3 inside and subtract 2 up here. So I'm going to be adding 2 down here at the base. And so this is 3cn minus 2 x to the n. Now, I want to combine them, so I need to have them both starting at 2, not one starting at 0 and one starting at 2. So I'm going to cull out the first 2 terms of this guy. So I'm going to call this cull. Bring out, when n is 0, we get c1. And then when n is 1, we get 2c2x. And then the rest of the power series is just 2 to infinity, n plus 1, cn plus 1, x to the n. And then this one, n equals 2 to infinity, 3, cn minus 2, x to the n. Now I can combine. Okay, so I just copy down C1, 2C2X, and now I've got a single power series that starts at 2, and I combine the coefficients. So I'm going to need a bracket, n plus 1, Cn plus 1, plus 3, Cn minus 2, x to the n. Now, on the next page, when we do this, we're going to start skipping this middle step. Well, not skipping it, but doing the cull and the combine at once. So I'm fine if you can go straight from line 1 to line 3. You're going to cull out the first 2 terms in your head. You say, okay, there's the first 2 terms, and then these are going to both start at 2 and then combine. It saves a line, and you might think, well, big deal, saves a line, but as you'll see on the next page, there's going to be a lot of lines, and they're going to be long lines, and so saving a line can sometimes be helpful. Now, if skipping that culling step screws you up, don't do it. Write it down. It doesn't hurt to write it down. It never hurts to write it down, but you don't need to if you don't have to. Okay, term-by-term differentiation. If you've got a power series, f of x is represented by this power series function, and it has a radius of convergence r, then you can differentiate and integrate term by term, and you will not change the radius of convergence. The interval of convergence might change, but the radius won't. So what does that mean? Well, here's f. Starts at 0, goes to infinity, cn x to the n. If I want to differentiate f, I can just differentiate using the good old-fashioned rules of differentiation. I bring the n down, that's this. Cn is constant, it sits there, and then I subtract 1 from the exponent. That's the power rule for differentiation. Notice, though, I have it written twice, one starting at 0 and one starting at 1. That's because when n is 0, the first term here is 0, and so why not just start it at 1? And so that's what we're going to do. We're going to go straight from f to f prime, and we're going to skip this step where n equals 0. So that's comment 1 here. We're going to go straight to the last form when we write down our derivatives. Now for the second derivative, I take the derivative of the first. I take this n minus 1, and I bring it down. It's right there. So now I have n times n minus 1. Cn's constant. It sits there. Subtract 1 from the exponent, and you have n minus 2. The n equals 0 and the n equal 1 terms vanish, so we may as well start at 2. So we're going to start our power series like that. And these rules here I've stated for a power series centered at 0, but comment 2 says the same rules apply for a power series centered at x0. So let's just do a couple of examples here. Find g prime and g double prime. Here's g. So g prime is going to be sum n equal 1 to infinity. I'm going to bring the n down. N times n squared is n cubed. Cn sits there. Subtract 1 from the exponent, n minus 1. And then g double prime. Bring the m minus 1 down. Well, first I have to write my summation. N equals 2 to infinity. N cubed. Bring the n minus 1 down. Cn sits there. X to the n minus 2. So pretty straightforward. Next one's got a factorial in it. So g prime. Bring the n down. Sum n equals 1 to infinity of Cn times n over n factorial. That's going to be Cn over n minus 1 factorial. So what did I do there? I had n over n factorial. I just simplified that to 1 over n minus 1 factorial. So that's my coefficient, and then I'll have x minus 1 to the n minus 1. And then g double prime, start at 2, bring the n minus 1 down, so I'm going to have n minus 1 over n minus 1 factorial. That's n minus 2 factorial. X minus 1 to the n minus 2. All right. So now we're going to start getting into the first half of solving a differential equation with power series. So on this page, we're going to do 2 examples. Well, I'm going to do one, and then you're going to do pause and practice, and you're going to do one. We want to write the expression given as a single power series in x to the n. And we're told that y is sum n equals 0 to infinity of Cn x to the n. So the first thing I do when I'm solving a problem like this, I write down my derivatives. So I like to rewrite y even though it's already given to me. N equals 0 to infinity of Cn x to the n. And then y prime, take the derivative of y, start at 1, bring the n down, n Cn, subtract 1 from the exponent, x to the n minus 1. And then y double prime is going to be n equal 2 to infinity, n times n minus 1, Cn x to the n minus 2. Okay, now we're going to plug in. So in this expression up here, I'm going to put in my y double prime and my y prime. So I get 2 sum n equals 2 to infinity of n minus 1 Cn x to the n minus 2 plus 1 minus x times the sum, y prime, n equals 1 to infinity n Cn x to the n minus 1. Now, every problem is going to start with step 1 the same, derivatives, and they'll be the same every time, but don't skip step 1. It's really helpful to your reader. It's also really helpful to you as you're doing the plug-in step to refer to your y prime and your y double prime and not doing it from memory. Okay, next step is distribute. I'm going to take the 2 and bring it in. Not much to do there. 2n times n minus 1 Cn x to the n minus 2 plus, now here when I distribute, I'm going to get 2 different power series. The first one is just this one because I'm multiplying by 1. So n equals 1 to infinity of n Cn x to the n minus 1, and then minus the sum. When I multiply this power series by x, the only thing that's going to change is the exponent will be n, not n minus 1, because x is x to the 1, and you're going to add the exponents. So this next power series will be 1 to infinity n Cn x to the n. Okay, so now I'm going to re-index. What needs to be done? The last guy's okay. The first two guys need to be re-indexed because they need to be written in x to the n. So for the first guy, I want to add 2 up here. So I'm going to subtract 2 down at my base. So I'll have 2, n plus 2, n plus 1, Cn plus 2, x to the n. And then the next one's going to start at 0. And it's going to be, let's see, I need to add 1, n plus 1, Cn plus 1, x to the n. And then I'm just going to copy down the third power series because it's not going to change. Okay, now I'm going to cull and combine, which I'll just call combine. You can see now, maybe culling, writing down a whole extra step for culling isn't so wise. So when I cull and combine, I'm looking at these 3 power series. 2 start at 0, 1 starts at 1. That means I need to start them all at 1. I need to start them at the highest value of the 3, which is 1. That means I need to cull off the 0 term from this guy and this guy. So the 0 term from the first guy is 4c2, and then the 0 term from the next guy over is c1. All right, now I can write them all as starting at 1, n equals 1 to infinity, and I'm going to combine these 3 by combining the coefficients. So I need a big set of brackets, and I'm looking at my coefficients. Before I write down, I'm just saying, do I have to combine any coefficients? This is n plus 2, n plus 1, and n. So none of the c's are in common, so I don't have to combine any coefficients. So I just write down literally these 3 coefficients: 2, n plus 2, n plus 1, Cn plus 2, and then plus n plus 1, Cn plus 1, and then minus n Cn, close bracket, all of those times x to the n. And there we have it. Okay, pause and practice. You guys try one. All right, I'll go through this fairly quick. Remember, you can always slow me down, or if I'm going too slow, you can speed me up. N equals 0 to infinity of Cn x to the n. So I'm writing down my derivatives. N equals 1 to infinity of n Cn x to the n minus 1. And then double prime is 2 to infinity n minus 1 Cn x to the n minus 2. Okay, plug in. I'll just call that plug, which I can't spell. Plug. Y double prime. Sum n equals 2 to infinity of n minus 1 Cn x to the n minus 2 minus 2x squared times the sum n equals 0 to infinity Cn x to the n. Distribute. N equals 2 to infinity. So I'm leaving the first one alone. Cn x to the n minus 2 minus the sum n equals 0 to infinity of 2Cn x to the n plus 2. All right. Now I need to reindex, and I'm going to need to reindex them both. Okay, this one starts at n, this is in n minus 2, so I'm going to add 2 here, so I'm going to subtract 2 down at the base. So the first one's going to start at 0, and it's going to go n plus 2, n plus 1, cn plus 2, x to the n, and then minus some. This one I need to subtract 2, so down here I need to add 2 to infinity of 2 cn minus 2 x to the n. All right, and then the last step, cull and combine. This one starts at 2, this one starts at 0, so I need to start them both at 2. That means I need to pull out the 0 and the 1 term from this first guy. So that gives me 2c2 plus 6c3x plus, now I can combine them, n equals 2 to infinity. The c's are different, so big bracket, n plus 2, n plus 1, cn plus 2, minus 2 cn minus 2, close bracket, x to the n. And there we have it. All right, so now I'm going to give you a preview of what we're going to do with this next time. And I'm going to give a preview with a first order differential equation. And so how do you take what we've done here and use it to solve a differential equation? So I've written down most of the steps so I can just talk you through this and you don't have to write anything down. And then I have one for you to do at the end with the solution at the end. And then finally, I have a little bit about analytic functions here. Analytic functions are the best of the best. And so I've nested all the types of functions we have here in a picture, and you can see where analytic functions lay. I just mentioned that because the word analytic is going to come up in the next section. All right, so where am I? Okay, this example. I want to solve a differential equation, and I'm going to do that by finding a power series solution. So I'm going to assume that y is a power series, and I want the first 4 terms. So I'm going to go up to C3 because y is going to be, if I write this out, that's C0, C1x, C2x squared, C3x cubed plus ... I need to find those c's, C0, C1, C2, and C3. How do I do that? Well, the first half of the solution is going to be just like what we've been doing. 1, write down your derivatives. So if y is this power series, then I only need y prime. I don't need y double prime because this is a first order differential equation. 2, plug in. So what's new here, I just plugged in y prime here, minus 5. This is y prime, and this is y. What's new is equals 0. Before, we just had an expression up here. There's no equal 0. We just had an expression, not an equation. Now I've got equations. So this is new. But up to here, this is old, what we did on the previous page. And then past that is new. So the old stuff, once you plug in, you reindex, and then you combine. In this case, I didn't have to cull because after I plugged in and reindexed, these both started at 0. So you can just walk yourself through this. You can just pause the video and make sure that you're following along. So now let's jump to the new stuff. I've got this differential equation, so the power series expression is equal 0. That means, I don't know if you remember from last time, but if you have a power series set equal to 0, that means all the coefficients are 0. So I set each of these coefficients equal to 0. So this is the coefficient. I pull it out and I set it equal to 0. And that's going to be true for n equals 0, 1, 2, up to infinity, because this summation starts at 0. Then I solve for the higher c's in terms of the lower. So I solve for cn plus 1 in terms of cn. Pull the 5cn to 5c is this a, there's a typo there. This should be CN, N. And so that should be, move the 5CN over and divide by N plus 1. So I fixed it here, but for some reason it's a C5 there. Should be a CN. I'll go in and fix that later. So I might even have it fixed by the time I upload these lecture notes. All right, step 6. We're now ready to solve for what these C's are. So we start just literally plugging N in to this equation. This is called the recurrence relation. When N is 0, that gives me the equation C1 is 5 C0. All right. When N is 1, C2 is 5 halves C1. But you know C1. C1 is 5 C0. This is why it's called a recurrence relation. Each C is written in terms of the one before it, which can be written then in terms of ones before that. So I'm going to be able to write all my C's in terms of C0. Finally, when N is 2, I get C3 is 5/3 C2. Plugging in what C2 is, that gives me 125 over 6 C0. Okay, now remember, we started this by assuming that Y looked like this. This is the generic formula for Y, and I really suggest you write this step down, because students that don't write this step down, they skip right to try and write down the answer. They often make a mistake. So here's my generic formula for Y. And now I'm going to plug in the C's that I know. C0 is C0. C1, though, is, where is it? 5 C0. So 5 C0 X. And then C2 goes with X squared. C2 is 25 halves C0 X squared. And then C3 is 125 over 6 C0 X cubed. And then you'll keep going, but we're not going to, because we're told to stop at C3. That's a C3. All right, now I can pull out the C0. No, it's not a C3. It's a C0. I can't read my own writing. The whole point was to write all these in terms of C0. All right, so Y equals, pull out the C0, 1 plus 5X plus 25 halves X squared plus 125 over 6 X cubed plus ... There's our power series solution. Okay, and so just curious here, we didn't have to solve this by using a power series. The original differential equation was y prime minus 5y equals 0. So I can rewrite that as y prime equals 5y. That's dy dx is 5y. And then that gives me, if I separate the variables, 1 over y dy is 5 dx. Integrate both sides, ... You're going to get y equals a e to the 5x if you solve this by separation of variables, which we did like the first or second week. Well, how does that jive with, I use the word jive, how does that jive with what I have above? Well, it's the same thing. The power series representation for e to the x is the sum, n equals 0 to infinity, of x to the n over n factorial. So if you have a 5x, you just replace x here with 5x and use parentheses, of course, and you get this. The sum, n equals 0 to infinity of 5x to the n over n factorial. Well, that's exactly what I have right here. If you expand this, do the first few terms, you'll have exactly what I have here. So it's no different from the old solution, it just looks different. Okay, in the next section, we'll solve slightly harder differential equations.